Okay, well, welcome back, everyone. So hopefully you've had some interesting discussions in the breakout rooms. And so now we're moving on to talks from industry to understand some of the things that are going on in the sector that we might be interested in and want to pick up on in our own teaching. We've had, unfortunately, apologies from Chandra from CGI. She's unwell today, so she won't be able to join us. But we do have Stuart from SJE Space, Mike from Oxford Dynamics, and Rosie from Skyrora for their talks. And then we'll have a panel discussion at the end. So I think without further ado, I'll hand over to Stuart.
Okay. Good afternoon. Thank you very much for the invitation to speak. I've been working as a consultant in the space industry for about 4 years now, having previously spent 16 years with the MOD and 14 years with Surrey Satellite Technology. And one of the things that I've been doing while I've been a consultant is working with the Global Network on Sustainability in Space, which is an STFC funded forum for interaction between the academic sector and industry. And so I hope that I can bring some of that sort of perspective to the talk this afternoon. Obviously, as we heard earlier, quite a lot of different sources of space debris that we have to worry about. There's the large stuff, which are generally in the catalogue, defunct satellites, rocket bodies, occasionally deployment debris, such as the nose cone that was released when the Russians launched Sputnik. But then there have been a lot of other sources of debris that have created a lot of much smaller stuff. So collisions such as the Iridium Cosmos collision that took place sadly, some self-fragmentation events from objects that either had batteries that overcharged or residual propellant that exploded. We've had anti-satellite weapon tests from various nations which have generated debris. And I think it's also worth mentioning that satellites in low Earth orbit are not just in a benign environment. They are actually potentially subject to sort of pebble dashing by micrometeorites coming from the natural environment. And we know that this occurs because we've seen evidence from objects that have re-entered, such as the picture bottom right of a rocket body with a hole that was neatly punched in it by a micrometeorite. So there's quite a bit of a debate about how much stuff is actually in orbit around the Earth. So the catalogue of 10 centimetre sized objects is sort of on the order of about 30,000 objects, but we're pretty confident that there is a much larger population of even smaller stuff. And the difficulty is understanding quite how much of that stuff there is actually up there. So this is an ESA slide, and you'll see that on this slide, the ESA number for the number of 1 centimetre and larger objects is on the order of 900,000. But if you ask the same question of NASA, you'll get a very different answer. NASA's estimate for that number is around 500,000, so nearly a factor of 2 different. And it's that level of uncertainty that's causing us a lot of problems, because you might feel that you would like to try and avoid getting into a situation where the debris starts creating a runaway effect, the so-called Kessler syndrome. Well, the Kessler syndrome depends on the density of objects in various orbits, but until we get a good number for those densities, we don't know how close we are to those runaway effects. So we do have to improve our ability to track stuff, especially the small stuff. Another area of uncertainty is exactly how long some of this small stuff stays in orbit. So we're reasonably well able to assess the lifetimes of large objects because they're easy to track, and we can see the rate at which they're approaching the Earth's atmosphere and burning up. But it's harder for the small stuff because, again, we're not able to directly observe it, so we have to extrapolate what it's likely to be doing. And some of those extrapolations suggest that actually there's cause for optimism, because the lifetimes of the very small stuff is actually quite short, measured in days and weeks and months rather than years and decades. And the reason for that is because the ballistic coefficient is different. So the very small stuff has a ballistic coefficient that essentially allows the solar wind to get at the particles and make their orbits more eccentric. And then when their perigee gets low enough, they start to re-enter fairly rapidly. So that's cause for optimism, but we don't really know exactly how long those lifetimes are because we haven't actually measured them very accurately. So to their credit, ESA are planning a small debris characterization mission. The idea is to put up a satellite with something that looks remarkably like a drag sail, deploy it, and then create a large target, a large witness plate, if you like, in low Earth orbit. And ESA's original concept was to monitor any holes that might appear in that drag sail caused by small pieces of debris passing through it. I think it's probably likely that if you've got a large structure like that, that you may also see effects on the orbit and the orientation of that drag sail if it's hit by something. And again, if you can correlate those changes in attitude or orbit, you may be able to learn something more about the particle that may have hit you. But you face a challenge. We know where the big stuff is. The plot lower right sort of is all the tracked debris, and we know what altitudes most of those are. It may well be that there is smaller stuff, and that because of the shorter lifetimes associated with smaller stuff, it may be that some of that material has already approached the Earth to a greater extent. So the peaks of the very small debris may actually be closer to the planet than the larger tracked population. We're still trying to work that out, and hopefully we'll start to get some sort of handle on this via this ESA mission. But I would point out that it's just, one mission at one orbit, and I don't even know if they've chosen which orbit altitude to go and measure at the moment. So what we're worried about is the way that the debris evolves. Martha put up a version of this plot earlier, but I'd like to draw your attention to a couple of different aspects of it. One is that even if we conduct good post-mission disposal, the debris population will increase. So the green and blue lines at the bottom of the chart do continue to result in more objects in orbit around the Earth. The reason being that, even if we're disposing of our active satellites, there is an existing debris population that by the laws of statistics will collide and will generate more debris objects over time if we do no debris removal. The other thing that's slightly worrying, I think, is that if you look at those graphs carefully, you'll notice that there's a sort of sinusoidal ripple on them. That sinusoidal ripple has a period of 11 years and corresponds to the solar cycle. And what's being modeled here is the helpful effect that the sun has when it gets to the peak of its activity. It expands the atmosphere, and that additional drag on stuff in low Earth orbit causes things to re-enter. So we end up with a slightly smaller debris population. The concern, I think, is that the sun's long-term behavior is a bit unreliable. There was a period between 1650 and 1720 known as the Maunder minimum, where the sun was very low in terms of its activity, very few sunspots. And if we do go into another period of relatively quiescent solar activity, we could find that we end up on one of these orange or red curves, whatever we do, because the sun isn't helping us out by causing some of the debris to re-enter. So there are debris removal projects. We saw some video on the UK ESA presentation earlier. This is deliberately a very busy slide because every time I hear about a new technique for getting rid of debris, I put a picture of it on this slide and squeeze the others up to make room. It's to try and make a point that nobody has yet come up with the perfect solution to debris removal. There are some techniques that work in certain circumstances and some that work in others, but there doesn't seem to be a universal panacea. But even if we can solve the technical problems, there are still some interesting political hurdles. A a lot of these technologies look like space weapons in the wrong hands, and there is no equivalent to the law of salvage in space at the moment. So if you go and interact with somebody else's rocket body or something else in space, potentially that's a diplomatic incident. And the final piece, which I think is perhaps the hardest problem to solve, is actually who pays for this. We've ended up with a sort of traditional tragedy of the commons situation where we've made a big mess and nobody really wants to pay the costs of clearing it up. There have been some practical trials, so there is some cause for optimism. It's still a complex problem, and actually getting objects that weren't designed to be sort of brought under control into a situation where you can safely deorbit them or dispose of them in some way is not trivial by any means. But imagine that we've created a debris removal system. We now have to take some decisions about the sort of things that we might wish to get out of orbit. What are the objects that we should focus on? ESA's focus is on the ENVISAT mission, the picture top right, because it represents about 7 tons of embarrassingly non-functional ESA hardware that they would like to deal with in a more responsible fashion. But ultimately, when you've looked at various of the problems, including whether these things are tumbling and rotating and whether they're difficult shapes, one of the key things that you have to take into account is the number of other objects that the object might interact with and the amount of debris that it might generate depending on its size. So some people like Darren McKnight, who now works for Leo Labs, have done some calculations of this sort of risk probability, if you like, and the conclusion that they've reached is that Zenit or SL-16 Russian rocket bodies are definitely the worst potential offenders up there. There are quite a lot of them. They're thought to weigh about 9 tons each, so if 2 of them were to collide, potentially you've got about 18 tons of debris. And Darren's quote is, that would double the tracked population of space objects overnight. I think that's a bit optimistic because I don't think our tracking network would manage to get all those objects into the catalogue overnight. But nevertheless, there would be a very large number of uncorrelated targets whizzing around that would cause us a problem. But it then occurred to me that perhaps we could use space debris against itself, in the sense that although that ESA mission that I was talking about just now is just one satellite in one orbit, some of these large hazardous rocket bodies are actually effectively witness plates that have been in space for quite a long time. If we were planning debris removal missions to try and deal with these high-risk objects, perhaps the first thing to do before we actually attempt to deorbit them would be to actually conduct some sort of observation campaign against them by taking pictures of them to see how many dents and holes there are in the rocket bodies themselves, because I think the rocket bodies potentially can tell us something about the debris population that they've been flying through. We know what orbits they've been in because they're large and have been tracked pretty much continuously since launch. We know what their physical size are. We have some idea of the motions that they've been performing. So in theory, at least, we should be able to learn a bit more about the debris population from looking at different rocket bodies in different orbits around the Earth. Now, you've got a problem that is starting to percolate into the public consciousness when you even start to see Dilbert cartoons about the issues that you're dealing with. I hope that none of the mega constellation operators are actually aiming for cities that have lots of swimming pools, but clearly this is definitely not the future we want. And one of the issues that has started to be raised recently is whether we should actually be trying to deorbit objects into the Earth's atmosphere at all. And the concern goes like this, that obviously there is a lot of natural meteoritic material that hits the Earth every day, but most of that is iron, rock, and some water. Whereas in the case of satellite material, far less of it, maybe only 2 tons per day, but a lot of that material is aluminium, which has the potential to interact with the Earth's upper atmosphere, generating aluminium oxide, alumina, which has reflective properties that may start to affect the balance of the behavior of the upper atmosphere. And it may also start to damage the ozone layer. And we saw, the effect of chlorofluorocarbons a couple of decades ago, and we don't really want to get back into that sort of situation. So is there an alternative? Well, there have been some interesting suggestions from a couple of my colleagues at the British Interplanetary Society. Mark Hempsell and Roger Longstaff came up with this idea that they called a necropolis, but it's essentially a space junkyard. The idea is that it's a managed facility in orbit, and when your satellite gets old, you can take your satellite and bolt it onto this and passivate it, and the necropolis will take care of keeping it out of harm's way. It's potentially also possible to think of this as some sort of destination for space tugs. If we do have debris removal missions, they could capture objects and then take them to the necropolis rather than deorbiting stuff into the Earth's atmosphere. And in the sort of rose-tinted future, you might even imagine that this sort of facility could then start to reprocess materials. If we can start recycling material, a necropolis might be the place to do it. So final question I wanted to leave you with is there an upside to space debris? So this is the cartoonist's version of that question. This debris field looks a bit like the debris field around the Earth in the kids' movie WALL-E, if you've ever seen it. Fortunately, we're fairly confident that the debris population is nowhere near as close as that. But we probably can't reverse global warming by putting lots of debris in Earth orbit. But what we might be able to do is recycle the debris. So as I mentioned, a lot of the debris from satellites is aluminium, and there's a team in Australia, a company called Newman Space, that is developing thrusters that work by using metals as propellants. So you can use a variety of different metals, but aluminium is one. And what you do is you make a fuel rod out of aluminium, you hit it with a very large spark, and that ionizes the metal. And then you can accelerate those ions out of the back of the spacecraft, rather like conventional ion thrusters today. It's just that you're using metal ions rather than xenon gas ions as your propellant. Interestingly, that kind of changes the game, because now the space debris then becomes an on-orbit resource rather than just solely a problem. And the data about where suitable items of space debris are actually becomes very useful data. It increases the value of the space traffic control information that we collect. There are some legal implications. There are various treaties that talk about things like the responsible use of space, and we would have to get an agreement that disposing of satellites in this way is a responsible use of space. There's quite a lot of this debris in the size range 1 to 10 centimeters, which hasn't been tracked for a long time, and which I call grey debris, because even if we do manage to get it into the catalogue, it's not clear whether we would be able to assign it to any particular nation state that launched it. So we need to understand from a legal perspective how we're going to address that unclaimed debris. We would need to establish whether, if somebody wanted to salvage a rocket body in space, whether there's some transfer of ownership and legal rights associated with that. And if you do actually interact with some object on orbit, are you responsible for it thereafter, i.e. you've affected its orbit, are you then potentially legally liable if it bumps into something? But if we can get to the end of that process with the help of the lawyers and with a better space traffic control system, I think there's at least a couple of ways here which we could use the debris population against itself, both to provide us information about the small debris population and then possibly as a source of fuel for missions that might in the future spend their time in LEO going to a space junkyard, collecting fuel rods, going to collect another piece of debris and completing the cycle. So we may be able to avoid the nightmare scenario that I referred to in the movie WALL-E. And at that point, I'll stop. And if you have any questions, I'm happy to take them in the panel session in a minute. Thank you very much.
Thank you very much, Stuart. So yeah, there's been some interesting comments in the chat, so we will certainly come back to those, particularly around the ideas of recycling stuff in space. I think that will be a very interesting discussion to come back to.